Just a second. Whoops. Lights. All right. Just a couple comments about the exam. Uh, every once in a while, I don't have any clicker items on the exam, and when that is the case, the percentage on the printout is accurate. For those of you, there may be a few of you, Leland and others, that don't have your printout. We'll catch you after class. And I'll publish or make visible the exam Scantron score. So we only have one score, and it's going to go under exam 2. And it's just all Scantron dots this time. And every once in a while, that's what I do. No particular reason. I like to do clicking questions, but they're not always appropriate. And so last time was a case of that. I don't know what the exam average is. We just got the printouts back this morning, but I'll try to tell you about that on Thursday, and so you can figure stuff out. I will say this: here's what I think you can do. Most of you have a printout. I guess maybe a few of you were absent, but if you have your printout, and if you remember your previous grade for exam 1, add them together. And if they're greater than 75, that's sum, if it's greater than 75, then that means on the basis of your 2 exams, if I were going to give a letter grade, I would give you a B. Okay, if this were the end of the semester and we just had 2 exams, no homework, no clicking, that would be a B. 75% or higher. All right? If you're above 90%, you're cooking with gas. I mean, you're really looking good. Now, in addition to that, let me point something out to you. If you do have 75 out of 100 between the first 2 midterms, you're going to get another 50 points with homework and participation clicked in together. All right, now we've already made an estimate of your clicking pointage a few weeks ago. I'll try to do that again this week. I'll also try to do an masteringastronomy.com roundup. That figure that's in there is several weeks old, so it needs to be replaced. But for many of you, you will be getting 25 out of 25 on homework, or close to it, 24 out of 25 on homework. Similarly, for those of you that are in class every day, and as you know, I can recognize many of you by name and by face for sure, and I know that you're here pretty much every day. And if you are here every day and clicking every day, you're going to have 25 out of 25. Even if you've maybe been absent for 1 or even 2 exams, you might have 25 out of 25 right now. And we never know what your clicking pointage or your homework pointage is for your semester grade until the very end of the semester. But right now you can estimate it. And I'd like to point something out that, and you maybe want to make a note of this, if you do have 75%, add 50 to that. That's 125. Now, if somebody has a calculator, can you do that quotient? 125 divided by 150. It's going to be 80-something percent. 83%. All right. So 83% is a solid B. And 135 is 90% of 150, and that would be an A. So now, here's the other thing. That's just with straight pointage, participation, and homework and exams. Now, if you've been to the observatory, add that to the numerator. So if you have 125, say, out of 150, add that another 10 points from observatory time. That puts you right at 135. Nice. All right. Now, some of you guys have bagged 2 or 3 observatory trips. Add 30. What the? If you have, oh man, I don't know. This is backfiring on me. If you have 125 at 150 and you add 30, I can see a guy up here in the second row laughing. That must apply to you. If you have, that makes your grade 155 out of 50. You're over 100%. You're breaking the system. Anyways, that would be an A. Okay, too bad I can't give an A plus. But anyways, if the bottom line is, or my last comment is, if you are feeling a little bit of the heat from your exam grades, every time you can nab some bonus points alleviates that just by 10 points at a time if you're going to the observatory. Right? Now, has anybody looked at the observatory sheet, Nights Under the Stars, today? Is it Thursday or Wednesday this week? Is it yellow or? No, not even yellow, just white. Oh boy. All right. So if it was tonight, it would be, did you see the sky outside? Man, it's clear as a bell. But we got to wait till Thursday. So hopefully you'll get a session in. Now, on the topic of bonus points, I know some of you can't make it to observatory because you work, or you ride the bus, and or you live in West Orlando, and coming back and forth is a impossibility. We'll have some other bonus point opportunities toward the end of the semester by way of review assignments that I'll set up traditionally in the last week of the semester to get you ready for the final. Also, I sometimes put more than 50 points on a midterm. So sometimes the clicking portion will take you up to 50, and then another 2 points above that, or another 3 points possible. So if you get all the clicking, you actually get 53 out of 50. So that's possible for exam 3, also for the final. So if you've missed out, and I know that there's a bunch of you that have, I wish everybody could go. I wish we were in Montana, because Montana, you could go out many, many nights of any week and see beautiful constellations and everything. Great observing. But if you haven't, we'll get you some chances to get a few bonus points. Okay, question in the back. No, that is incorrect. I mean, I understand what you're asking. The question is, well, how many points have we got left? I mean, because we got 3 50-point midterms, and 2 of them are in the bag, and we're going to drop maybe 1 of them if you're here for all 3. If you're absent for 1, then that's the one that you drop. But if you're here for all 3, then we'll drop the lowest. But then everybody takes the final, and that's another 100 points. So that'll be 100 points between the first 2 and maybe the third midterm. And then another 100 for the final. And then another 100 for homework and stuff. Another 50 for homework and clicking. And then I think I got 10 for a graphing assignment that we're going to do, so a total of 360. So we got some stuff ahead of us. And in fact, Thursday we might be in position to get going on the graphing homework. All right, so I'll tell you about that. And you'll have a week or so to do it, so plenty of time to do it because it's kind of tricky what we normally do. Anyways, any other questions about grades and whatnot? Who had an 82? I can't even respond to that because if I did, I'd be violating your privacy. Anyways, let's get your clickers ready and let's do a clicking question concerning binary stars and binary star systems. I have a question for you. Hopefully, you will know the answer to this. We're on frequency AA. Go ahead and click. Go ahead and vote. Read carefully, though. Do not let me catch you napping. Yeah, put on your specs and take a look at it. 20 seconds. Ten seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see what you guys voted for. All right, let's just check this here. Yeah, a bunch of you voted for B. That is the correct answer. Yeah, there's no guy by the name of Raymond DeBinary. And D, binary data. Ooh, I nabbed a few of you with some juicy terms here. Information and black holes, information loss in black holes is a very complex topic, but it's not why we call it binary star systems. Binary star systems means it's a pair of stars that orbit their own common center of mass. If they're the same mass, then the center of mass is right in halfway between them. If they're unequal masses, then the center of mass is slightly closer to the heavier star. Anyway, majority of stars in our galaxy, so far as we can tell, are in binary star systems. Our sun is what they call a singleton. It's not part of a binary star system as far as we know. There's guys that are constantly on the alert for evidence that our star is actually in a gravitational interaction with one of its neighbors. We're pretty sure it's not in a gravitational interaction with, for instance, Alpha Centauri, any of those. That's a triple star system. But here's an example of Mizar. That's the middle star in the Big Dipper's handle. And you can see it from this diagram here. Alcor is its companion, and supposedly, I was reading about it this morning, getting ready for lecture. Alcor, if your vision is not like ultra 20/20 eagle eye sharp, you still might be able to see Alcor, or if it's a good dark, clear night. You know, it's like if you went up to Ocala National Forest somewhere tonight, I'm sure you could probably break out these babies if you could see the North Star and the Big Dipper. And by the way, these two stars out here, these are the two pointer stars. They point to the North Star. North Star would be down here to the lower left. Anyway, so that's a famous double star. And Mizar is actually two binary star systems. And the reason that we can see that is because we can analyze the light and see that there's a variation in the wavelengths caused by the Doppler effect. In other words, when a star is moving away from us, the hydrogen alpha line is a little bit redder than usual, a little bit longer wavelength. When it's moving toward us, for instance, the hydrogen alpha line is a little bit bluer than normal, so a little bit shorter wavelength. And we can measure that. We analyze the spectra and figure out what they call the Doppler shift by looking at, like H alpha, or maybe some of the lines of helium, or maybe the big bright sodium lines. Any kind of lines that you can get that you can compare to laboratory values, you can figure out a Doppler shift if there is one. And so if you see two things at the same point in the sky, one of them is Doppler shifted to the blue, one of them is coming towards you, Doppler shifted to the red, then you know that, and then if it changes, the same two things change, one of them changes to, you can't make them out spatially, but you can see two different things. And if they go from blue to red, both of them, then you've got a binary star, what we call a spectroscopic. You can't visually separate them and know that they're orbiting, like you can with Mizar and Alcor, but you can see it in their spectra. And anyways, Mizar is actually two, and Alcor is actually a binary system itself. So it's kind of a, so when I say that most of the stars in the galaxy, or the majority of the stars in the galaxy, are in binary star systems, I ain't just whistling Dixie, as the saying goes. Or astronomers are not just, whistling. I don't mean maybe. I mean there are buku binary stars. I mean, that's just one little piece of the Big Dipper, and it's loaded with binaries. Side note, kind of a beautiful thought. There's a river of stars through that entire part of the sky and that's part of the Ursa Major constellation. And that river of stars is called the Ursa Major Stream. And it's like a river. The stars have similar composition, and they seem to have similar velocities. They don't all have the same velocities, but they're all pointing in roughly the same direction, and they have similar speed ratings. The proper, or the technical term for that, is proper motion. When we look at a star and analyze its Doppler shift and measure it, if we can triangulate to it and get its distance accurately and actually see it change position on the sky, by, 1,000th of an arc second or so over a year or over a century, then we can figure out how fast it's actually moving, if we can find how far away it is. And that all factors into the proper motion. This group of stars is, they call it the Ursa Major Stream. The sun is not a member of it, so we're in it. It's flowing past us, but we're not a member of it. We have a different composition, and our star is heading across a stream or something. It's not part of this. The stream is all kind of moving in the same basic direction. It's lovely to think about. I love thinking about the Ursa Major Stream, and that's just one. There's zillions of these things that we can see in the universe. It's kind of interesting. We've analyzed those stars. We know they're all about the same age. They all have similar composition, and they're moving in the same direction. So for some reason, they seem to have been formed together, lit up as stars together with fusion. And that's the birthday. That's the birth of a star, when it starts nuclear fusion in the core. And they seem to be all moving in the same direction for whatever reason. Boy, we'd like to know that, but I don't think anybody's figured that out yet. A lot of times you can figure stuff out like that, but we haven't done that yet for the Ursa Major group. Now, binary stars, they're pretty important for us. It's a real important bit of leverage that we have for analyzing even as far as the most distant galaxy. The fact that we can triangulate the distance and then measure the orbit, using parallax. Basically, this This is figure 12.3 from your textbook. That's it, parallax angle. It's all in there. We've talked about that before. Your homework will be about parallax and distance and stuff tonight. And then if you use a regular calendar or a clock for timing the orbits, and if you know how far away they are, then you can use the Kepler third law to get their masses. Now, I'll just draw you back and make a reference to chapter 4, page 96, where they say that when they first introduce Newton's version of Kepler's third law, the fact that you can determine the masses of distant stars if they are members of binary systems. So go back and take a look at page 96 tonight when you're studying, and it'll help you. It's also mentioned in chapter 12 from page 312 and forward from there for a few pages. So look at 96 and then page 312 and so forth in your reading tonight about parallax. Knowing the mass of a star is really important. Now, any star that we can see, we can analyze the starlight, and we can figure out the spectrum. Looking at the spectrum, we know if it's got hydrogen, we know if it's got helium. Jacob, we know if it's got a little bit of oxygen or nitrogen in its atmosphere. And by judging the relative intensities and the temperature, we can kind of estimate, well, how much hydrogen have you got? You know, how much helium have you got? How much nitrogen? Is it loaded with carbon? You know, there are some stars that are carbon, they call them carbon stars. And we can deduce that by looking at the spectrum and a few other things. So if we can figure that out, and we can figure out the temperature, you know, by looking at the peak, you know, if we know the peak is over in ultraviolet, we know it's got a certain temperature. If the peak is in infrared, we know it's a little bit lower temperature. If the peak is at about 5800 green, then it's about the same temperature as the sun, surface temperature anyways. And if we know that, we can figure out luminosity, apparent brightness, and we can even figure out and model tentatively the nuclear reactions, Drew, that are happening in the center, in the core of that star. And all that stuff. And so, and the nice thing about astronomy is we got buku stars that we can analyze. I mean, right now we've got, I don't know, probably millions of stars that we can analyze in this way. We're really doing good. And so this is the reason that binary stars are important. If we can get, you know, the first few thousand light years from Earth, that's going to be a lot of stars. It's a good sample, hundreds of thousands of stars. If we can get those and figure out a pattern in those, which we can, then we can look at other galaxies, no matter how far away, and say, all right, probably the same formation processes, the same distribution of stars is going to hold in that galaxy that's, you know, billions of light years away. So parallax, Sarah, is pretty darn important, and binary stars are what make that important. Because if we can figure out the size of the orbit and their distance, we can always time it. The timing is not hard. If we can see the light from the star, we can time its variations. That's not too difficult. We want to do it as accurately as we can, of course. But it's not that hard. But getting the distance is hard. And if we can do that, boy, we could it's like a jigsaw puzzle. Once you know, if you've ever done a jigsaw puzzle, a tough one, and you're looking at it, and oh man, it's some fish from the Amazon that I've never heard of. But then once you figure out what it has to be, like the amua, A-M-U-A, it's some kind of fish in the Amazon or something, supposedly. And you figure that out, and then all of a sudden, everything else, the whole crossword puzzle, bing, you got it in about 2 minutes. It's kind of cool. And the same thing with getting um, a parallax measurement on a binary star system. And we got a lot of binary star systems, so it's working out nice. Here's I'll blow up a figure 12.3. Definitely, when you're studying tonight, when you're trying to do your HW, and your homework will start at 3 o'clock today. It's already set up for you. And it's not gigantic, but do your studying. Definitely eyeball this and read the text around this part of chapter 12, and that'll be good. Now, we're actually going to do some new stuff here. We'll come back to triangulation and parallax and stuff on Thursday. I want to dip back actually to chapter 5 where they talk about telescopes, but these telescopes are not in some of these are not in chapter 5. Okay, this is a picture of the Kepler telescope, the Kepler spacecraft, a recent telescope. I'm not sure it's in the textbook yet. So this is our next topic for today, tools for observing the stars. One of the best ones, Hipparcos. The Hipparcos satellite orbited Earth, and it made a bunch of very hundreds of thousands of stars, getting spectra and getting parallax. It was designed for very precise parallax measurements. So in other words, look at a star in June, look at it again at the end of December, and then figure out the difference in the tilt angle, the difference in the aim of your telescope, and that'll give you the parallax. And from that, you can figure out from the baseline of Earth's orbit how far away it is, plus or minus a little bit. Now, they say that from Earth orbit, Hipparcos could map the height of one of the Apollo astronauts standing on the moon, so 2 meters. That's pretty good. In other words, you could get the parallax measurement for an astronaut on the moon. And that's almost 250,000 miles away from Earth orbit. So that's pretty impressive. And that was 20 years ago in the 1990s when that baby was running. And we've got guys, they are still analyzing that data because Hipparcos picked up in all directions, just hundreds of thousands. It's an enormous catalog. Go ahead and write that word down, the Hipparcos catalog. And it's not something you order, a pair of sneakers from, or a new watch, or music. It's a catalog or a big data bank of all the measurements of all the stars the Hipparcos got. Now, here's another one. Hipparcos is good, but here's another new one. Kepler. Now, who was it that was asking me about the Kepler data bank? Are you here today? We got a student in a computer class that's working on that wants to analyze the Kepler data. Now, the Kepler, this is a picture of the spacecraft. It looks, to look at it from the side, it looks a little bit like the Hubble. It's kind of got that chiseled, angled opening. But Kepler's a little bit different. It stared not in all directions, but in a very particular direction. So it had a very small area that it was actually scanning. And these wheels down here, okay, these circular device, well, I don't know, that might be an antenna, I guess. But it has what we call stabilization wheels, and that keep it oriented in a particular direction. And there's other things that they use to keep it oriented toward a very particular slice of the Milky Way. And this one is optimized for finding exoplanets. In other words, planets around other star systems than our own. Alpha Centauri A, Alpha Centauri B, Alpha Centauri C, and everything out past those in all directions. And Kepler, and actually, they're not looking at Alpha Centauri, but they're looking in this particular direction. in the constellation Cygnus. So just slightly off from the plane of the Milky Way. You can see the Milky Way. This constellation Cygnus, Cygnus, that's Latin for swan. You can see the two wings of the swan. And then here's the long neck of the swan here. It's something you can see in the summer on a good clear night. And some people call it the Northern Cross because it's kind of a cross shaped. And I love it because a couple things. Cygnus, which we can't really see now, it's up during the day, I think. It's washed out by the sun. But in a few months, in the summer, you'll be able to see it. It's the summer cross, or the Northern Cross, summer constellation, and it's right aligned with the Milky Way. And I always like to tell students, just think of it as flying down the Milky Way. And that's the orientation of it. You can see it here. Also, in the constellation Cygnus, you can make a note of this. The very first X-ray source that we've tagged as a possible black hole is in Cygnus. And we're pretty sure now that it's a black hole, the very first one that we ever, you can't see a black hole, but you can see the black hole's effect on the orbits of things around it. We've talked about that before. And in this particular star system, there's a giant star orbiting something we can't see, and something that we can't see nearby it, it's emitting a lot of X-rays, and those are what we picked. That's what twigged us to this particular black hole candidate, and that's in Cygnus. It's called Cygnus X1. So go ahead and write that down. Kepler's looking in that direction, and here's another view of it. Here's the Kepler field of view, they call it. So it's just looking here. Now, Hipparchus was trying to get as many in all directions as it could, and it got hundreds of thousands. Kepler's looking for hundreds of thousands, but in this particular direction of the sky. So it's always aimed over there. Now, it's not looking right into the plane of the galaxy, because that's a little bit too much traffic. It's looking a little bit above the plane of the Milky Way galaxy. So it's a little bit above here. Here's the Milky Way, kind of slicing down through here. Here's the constellation Aquila, right down here. And constellation Vega. Now that's an important star as well. That's a summer star. It's up in the summer. Toward the end of the summer, it's right at the zenith. It's very easy to see. And that's an important star we'll talk about on Thursday. Anyway, so Kepler is designed to look for variations in light. Now, when we're looking at a star that is variable, we try to measure the intensity of the light that's coming from that star. And a chart of the ups and the downs of the light coming from that star is called a light curve. Okay, so there's a vocabulary term for you, light curve. It's it's like an EKG for the star's light. When the star's light is intense, the EKG level goes up. When it dims out a little bit, the EKG goes downward a little bit, and that's a light curve. And so what we're looking for with Kepler is repetitive dips in the light curve of a star. Most stars are going to have really stable light. It's going to be a flat line. Now that flat line is bad for a person on the EKG because that means you're dead. We don't want that. But for a star, it means just cooking along, baby. Nice steady light. But, if the Earth goes in front of the sun, or if the moon goes in front of the sun, we get an eclipse. We notice it. And from a distance, from many thousands of light years away, we can see other planets eclipsing a star. And that's what Kepler is designed to find. It's designed to measure very teeny dips in the light curve of a star caused by planets on a regular basis. And once we see that it's getting periodic dips, then we know, possibly a planet. If we can time it, if we can get the distance to it, we can figure out its mass. And that is what Kepler wants to do. Kepler wants to figure out, here's another picture of the Kepler Space Telescope. Reaching out, they figure about 3,000 light years that it can see stars well enough to get a parallax measurement and to see the light curves and to see possible, or as they say, objects of interest. You know, when they see a dip in a light curve for a star somewhere in this cone here, they think, oh, maybe we got a planet. And my wonderful students, it's exciting. They've bagged hundreds of planets. You know, it used to be like 20 years ago, before Kepler was put in space, you know, there's maybe a few exoplanets known. They are very difficult to find. Now we're getting them by the boatload from Kepler, and we ain't done. Kepler's still up there, you know, giving a, and we're still analyzing Kepler data. Matter of fact, you guys can analyze Kepler data. They have a public program that allows you to root through the data and find a planet. Wouldn't that be cool? If you found a planet and you could name it after yourself, you know, the planet Leland. Would that be cool? Or the planet, and just fill in your last name. That'd be excellent. And you could say, yep, I named it. It's mine. All the diamonds in this planet, if any, belong to me. So now, right now, there's a little bit of trouble with these reaction wheels down in Kepler. So it's, you know, no spacecraft lasts forever. But boy, has it gotten a lot of good data. Now, here's another one. And we'll finish with this, just a few more slides. Gaia launched in December 2013. And it is designed to do the same basic task as Hipparcos. Get the angular position, get some spectra, and get a proper motion measurement if possible, parallax distance. And then, you know, and then figure out all that's basically do the same thing that Hipparcos was doing. Get some spectra, some light curves, you know, figure out what's happening. But here's the difference between Hipparcos and Gaia. Hipparcos could observe accurately the difference between a 2-meter and a 3-meter tall object on the surface of the moon. You know, an astronaut and the lunar module, for instance, that was a few meters taller. Okay, they would be able to resolve those differences, be able to see with precision. You know, it wouldn't be blurred. So Hipparcos could do that. Here's what Gaia can do. From Earth orbit, Gaia can map the width of a button on the astronaut's shirt standing at Tranquility Base on the moon. Oh my goodness. So you have to ask yourself, well, if we've got a telescope that's that good, looking at the moon and measuring a guy's buttons, what if we turn that the other direction and look at the Russians? You know, instead of looking out into space, turn it around. So you guys, whenever you see something like this, figure that for every one that NASA has, that the CIA and the Department of Defense have about 5 of them at least or more. And they're all looking at the Russians. Anyway. We'll finish with this stuff on Monday. Homework is running in masteringastronomy.com in about 12 minutes. You're dismissed. I'll see you next time. And we'll finish with Gaia.
I've emailed you a couple times about the